As Hannah has said, my name is Meadhbh Moriarty, and I work for Marine Scotland Science as their Senior Aquatic Epidemiological Modeller. So first up, I'd like to extend my gratitude to Hannah for facilitating this webinar. I also know that we have a few budding scientists watching today with their mums and dads, so I've tailored this presentation for quite a general audience, and I've included lots of pictures from sampling trips thanks to my colleague Stuart Wallace. Now I have to give a disclaimer, all of these photos were taken on that one day when the sampling occurred in stunning conditions. And I'm told that that is the exception rather than it's the rule. I'm told it's usually rough and wet, and there's almost no photos from these days. I wonder why. So today I'm going to talk broadly about some of the work we have done in Loch Linnhe over the past few years and some of the work we have planned for the next year. And for the younger audience members, I have a few questions for you. So I want to know, can you tell me how many boats there are in this presentation and how many pictures of fish are there in this whole slideshow? And you can put your answers in the Zoom comments at the end. So I'd first and foremost like to acknowledge some of our current collaborators, as all of our work is made possible through collaborations with academic institutions, industry partners, and conservation groups. So now let me take you on a journey from your home offices to the beauty of the west coast of Scotland to Loch Linnhe, where the research I talk about today is based. Loch Linnhe spans about 60 kilometres from the town of Fort William down to the Sound of Mull in Firth in the south. This makes it Scotland's largest fjordic system, and the unique characteristics of Loch Linnhe systems has led it to be a study area for many research projects over the years. And researchers have spent years investigating things like the environmental conditions and looking closely at the impact of aquaculture in this area. I'm fairly new to this role, but my colleagues have previously published their research in many different journals, and I've highlighted a few recent papers. One of the ways that we can support a healthy environment and sustainable industry is through baseline research. And we are building on the vast amount of knowledge currently published here in Scotland and further afield. So one of my areas of work has been identifying and modelling factors that could inhibit production potential in order to support sustainable growth in the aquaculture industry. Another, which I'll talk about in detail today, is identifying how sea lice moves and disperses in Scottish waters in order to understand where lice concentrations are and how they might interact with both farmed and wild fish. Our overall goals as a group are to reduce losses, to reduce medicine use, to simplify management, and to produce more farmed fish in the best possible conditions while reducing environmental degradation. So one of the ways that we will help to achieve these goals is by evaluating where lice concentrations form under observed environmental forcing in order to advise on best practice in salmon farm management. This is really essential research because Atlantic salmon aquaculture industry is a really important contributor to the Scottish economy. It provides critical employment in remote areas of the country, as you'll see from this map of the fish farm locations in Scotland. It's all on the west coast in areas that are less developed than the bigger cities. In 2018, the farm gate value of Scottish salmon was 878 million, and the industry does want to continue to grow sustainably. Now, one constraint on sustainable growth to aquaculture is lice. So sea lice or salmon lice are ectoparasites. And that means they attach themselves onto the salmon or trout and then feed on the mucus, skin, and blood. So the first photo I've shown here is just showing just that, a little lice sat on a salmon. A high parasite load can cause diminished health to both wild and farmed fish. And when we speak about sea lice, we're normally talking about the species I've pictured here in the middle, Salmonis. And this guy is a salmon specialist. This makes it a major species of interest. We know it's ubiquitous, and that means it's found everywhere in the marine environment. This parasite called Caligus elongatus, because it is known to cause osmoregulatory stress and secondary infections. We know that the larval stages of sea lice are planktonic, and this means they can be transported by ocean currents, sometimes over considerable distances. Because lice is planktonic, neighbouring farms can interact. So interacting groups of farms share lice and coordinate management. And to help coordinate management, we need to know what groups of farms interact and how. So where are the sources of lice and where are the sinks for lice? And how do the sea lice from farms spread to vulnerable wild salmonids? Now, one of the tools that we have to help investigate these issues are coupled hydrodynamic dispersal models. There are a number of different particle tracking applications that we can couple with hydrodynamic models. So a hydrodynamic model aims to explain how water moves around in the ocean due to drivers like currents, winds, tidal excursions. It can also predict useful information like the temperature and salinity in the water. Marine Scotland Sciences Oceanography Group have developed our Scottish Shelf model in conjunction with academic partners. Prior to the development of the Scottish Shelf model, we used the POLCOMS model, while one of our academic partners, SAMS, has also developed their own WestComs model, which describes the hydrodynamics of the west coast of Scotland. So researchers like me use hydrodynamic models to drive particle tracking model, which then allows us to infer the distribution of lice in the system. So one of our current projects is to carry out a comprehensive comparison of model results with field data in order to take account of the uncertainties in the different models. And this will help us to validate the use of our Scottish Shelf model for predicting sea lice dispersal in Scotland. So using Loch Linnhe as a testing site, we will gain an understanding of the reasons behind the differences in the model results. So we'll do this by analysing model structures. And then we will investigate the inference gained from a multi-model ensemble prediction, which includes all available models. So we are using Loch Linnhe because we have loads of historic data collected in this area. So, like I said, one of our major goals is to validate and compare some coupled hydrodynamic dispersal models in Loch Linnhe. And in order to do this, we require comprehensive sampling in the loch. Now, I mentioned earlier that Loch Linnhe is Scotland's largest fjordic system. It is a really important area for the aquaculture industry. In 2018, there were 10 farms registered in the loch, with 2 farms in an adjacent loch. The consented biomass for farmed salmon in the whole system was 10,652 tonnes. And there are loads of important questions that we need to answer about how these farms impact on the wider environment and on the important and vulnerable wild fish populations in the area. The component to effectively answering these questions is to collect data in the field to verify the models we build are accurately reflecting the environment. When we sample for sea lice, we have a few tried and tested methods that we use, and this includes plankton toes and Sentinel cages. This picture is showing SEPA's vessel, Sir John Murray, which my colleagues used for all of the sampling in previous years when sampling could occur. So here is some of the equipment waiting to be deployed at a station. So you've got plankton nets on the left and a Sentinel cage on the right. Other information, like currents, is collected using a vessel-mounted acoustic Doppler current profiler. So here are some of the fish from a Sentinel cage study in Loch Linnhe. 10 cages were deployed in May 2011. Each cage was stocked with 50 smolts obtained from Marine Harvest Scotland. These fish are left unfed before stocking, and then the fish are removed and the cages are restocked after 7 days. One of the cages was lost, while another cage experienced complete mortality of the stocked fish due to severe weather conditions, which were winds exceeding 80 miles per hour. Remember I told you at the start that all my lovely pictures were taken on a nice day? This is really just to highlight how vital the importance that information that we collected and how difficult it really is to get. So my colleague, Stuart, took a photo of these smolts during the sampling trip, and he was interested in counting how many lice are on these fish after spending 7 days in our Sentinel cage. So to give you an idea of the numbers of lice we found, the mean number of lice sampled across all the recovered cages was about 16 plus or minus 12. And this gave a mean abundance of 0.33 plus or minus about 0.29 settled lice per fish. The counts of sea lice were really quite low in 2011, and the counts on the cage fish were substantially below the treatment recommendations as stipulated by the Code of Good Practice within the industry. So here's another question for the budding biologists listening today. Can you spot lice on this fish? Let me know if you spotted it in the Zoom comments. Now, I can't take credit for the vitally important sampling work that Marine Scotland scientists do in partnership with the fisheries trusts and academic partners, but I do need this information to do my job, which is building, validating, and analysing models, and then effectively communicating the results to policy, industry, academics, and importantly, the wider public, so that we can all become ocean literate. So this is where my job really comes in. And a coupled hydrodynamic and particle tracking model follows a standardized framework which can be outlined in a 12-step program. Possibly not the 12-step program that we'll all need at the end of this lockdown, but let's continue through it. In the blue box, we have the work carried out by the Oceanographic Group at Marine Scotland Science. And in the orange box is the work led by the Health and Welfare Group, where I work. The Scottish Shelf Model is an unstructured grid, three-dimensional, finite volume community ocean model, or FVCOM. And this was developed specifically for Marine Scotland Science. The Scottish Shelf Model consists of a wider domain coarser resolution model, which covers the whole of the Scottish coast, the whole of the Scottish continental shelf, as well as a number of higher resolution submodels in some of the areas of that domain. And that includes the Loch Linnhe, the wider Loch Linnhe system, which is our current study area. So step 2, I've labeled model input. Excuse me. And this represents the extensive data that underpins the hydrodynamic model. This includes things like boundary forcing, atmospheric forcing, and freshwater forcing. The hydrodynamic model has undergone extensive validation, and I've highlighted this at step 3. For example, Rabin Hitson 2017 provide a detailed description of the physical data that were used to evaluate the circulation of Loch Linnhe for the wider Loch Linnhe shelf model. This is where I then come in at step 4, And the particle tracking, what happens then is the hydrodynamic model is coupled with a particle tracking model. And the particle tracking application that I use is a Langerian particle tracking model, which is an FVCOM I-state configuration model, or FVCOM, that was developed by Liu et al. 2015. And this is just one of many particle tracking applications that can be used to model the dispersal of sea lice rates in Scotland. So the idea is the surface currents are obtained using the hydrodynamic model. And what happens is that the lice representative particles move within the system. And the code tracks the released virtual particles representing the copiopods, and that's forced by the hydrodynamic model outputs. So at step 6, I've labeled this biological parameters. And it's really important that we understand the underlying biology of sea lice. And to do this, we need information on sea lice development, vertical dial migrations, mortality, and infection rates. And then this information is used along with the ingestion of the surface currents, and it's integrated with some diffusion, some horizontal dispersion, some stochasticity parameters in an equation in order to pull all this information together. So at step 7, we have the output. Now, the output of the coupled hydrodynamic and particle modeling is first validated using the data collected in the field to make sure it is reflective of the processes happening in the system. So biological validation of the model sea lice can be carried out in our study site, which is Loch Linnhe, where we have all of these plankton trawls and Sentinel cage deployments that have been undertaken throughout the loch system in previous years. So at step 9, we've got the investigation. And this only happens when we are confident that the output is meaningful and we have clear questions that we set out a priori that we want to answer. So the interpretation of our models requires visualization techniques, exploratory analysis, and we are developing model performance evaluation metrics and model comparison evaluation metrics to help us understand these outputs. So all of that work goes into putting together the underlying science for modelling sea lice dispersal in Scotland. And really what most people are going to be interested in is the applications. Now, there are numerous applications for coupled hydrodynamic and particle tracking models. We can look at farm connectivity. So is it symmetric or non-symmetric? Is the farm a source or a sink of lice? Can we approximate the magnitude of connections between sites? Can we predict sea lice pressure? And then can we correlate our metrics with the counts on farms? And how good are the model fits? Another application is in optimizing management areas. So at our study site in Loch Linnhe, we can assess the percentage of lice dispersed beyond the management area boundaries. And we can analyse management areas on a case-by-case basis for the Scottish coast. Now, I'm a statistician and a modeller at heart, so I feel the 12th step will always be talking about the assumptions and limitations, because with any modelling framework, we need to make a lot of assumptions. The underlying forcing files for salinity and temperature, for example, are point estimates, usually interpolated and smoothed over the grid. We are limited by our understanding of wild fish movements and our current understanding of sea lice biology and interactions. Now, this must always be considered when we investigate the data, especially when the applications can impact on management decisions. Now, I've just gone through the modelling framework we use for calculating potential distribution of sea lice in Loch Linnhe. Now, some say madness, is doing the same thing again and again and expecting a different outcome. But sometimes there is a need to look at lots of different models to gain a better inference to help answer a question. And this is because no one model captures all aspects of the biology, but a combination of models can sometimes give us a better idea of what is happening. So ensemble modeling approaches allow us to combine multiple models for better accuracy. And a multi-model ensemble is a set of model simulations from structurally different models. Now, studies indicate that combined information from several models can give superior inference than a single model. And the rationale behind that is if you generate a group of base learners with loads of different types of errors, when you combine them, you get a higher accuracy. So some of my colleagues in industry and academia have developed their own particle trafficking applications. So we have just started a new project to compare 3 different particle tracking models as our preliminary study. So what we will do is we will validate and assess them individually, and then we can create an ensemble model. In the first instance, we will use a simple multimodal ensemble prediction. In this method, predicted values from the different coupled hydrodynamic biological models are weighted equally to construct a multimodal ensemble prediction. So I'm going to just run through one model scenario under model framework A as example, because I'm working on model framework A, which is the FVCOM coupled with FVCOM. I have a colleague in industry who's working, I think he's listening today, he's working on model framework B. And then I have a colleague in academia who is working on model framework C. So our current project is to carry out a comprehensive comparison of model results with field data to take account of uncertainties in the different particle tracking models and to validate the use of our Scottish shelf model for predicting sea lice in Scotland. And then we want to compare and combine the different models to better understand the movement and the dispersal of lice in Scottish waters. Using Loch Linnhe as a testing site, we will gain an understanding of the reasons behind the differences in the model results. And by analysing the model structures, we will then investigate differences from multimodal ensemble prediction using all available models. So we are using Loch Linnhe because we have loads of historic data collected in this area. So on the slide now is one such model run as an example. And this is from the wider Loch Linnhe shelf FVCOM May 2011 run. As discussed, the preliminary comparison and validation. So this is really just the preliminary comparison validation with the results collected at this time. And in this model run, I have included some very simple lice biology. And the picture I've presented shows predicted areas of high and low densities over the simulation timeframe. So high is depicted in orange and low is depicted in blue. And as you can see, the main loch has a higher particle density on average than further out on the coast. So these results are very preliminary as we're still developing the underlying hydrodynamic models for these runs. So further model validations is required, but these modeling scenarios enable the establishment of general lice dispersal characteristics, such as areas of high and low density, like I showed in the previous slide. It also allows us to work out the transmission distances that consistently occur. So for example, copiapod in Nepal may be transmitted up to 30 kilometers away from source. So here I presented a partial plot of the maximum transition distance of particles from 4 of our 12 farms. So just to orientate you, frequency of released particles as a percentage of total particles is on the y-axis, and the distance travelled in meters is on the x-axis. So again, just these are very preliminary results, but it's nice to have a look at the differences between two different models. So my partial plot is on the right-hand side, and just by way of comparison, I've shown a run from earlier work carried out by my colleague Nabil using a different couple hydrodynamic particle tracking model in the same system. So that's shown on the left, and that shows all the sites. Now, my model is inferring that particles may travel further on average and almost twice as far in their maximum distance. And there are a number of reasons for this in terms of the model structure. For a start, the model domain I've used is larger than the one run by my colleague, and the underlying physical forcings are different. The biology applied for the particles may also differ. So my next job will be to look at which model gets us closer to real life. And this is just an example of the type of work we do. The framework that I showed you earlier will all have the same underlying hydrodynamics. And so the thing that we'll be interested first and foremost in understanding is the differences in the particle tracking model. But that work is just about to start, so it's a bit premature. So a combination of biological and physical models is required to understand the transmission of disease-causing organisms. And by developing descriptive simulation modeling frameworks, which are validated using both physical and biological observations from the field, we can then investigate and develop alternative methods of integrated pest management. The robust identification of dispersal routes of sea lice and establishment of potential farm-on-farm or farm-to-farm connections can also inform sea lice management. So, by way of summary, in order to gain an understanding of the reasons behind the differences in the model results, we need to analyze both the hydrodynamic model structures and particle tracking model structures. And our next steps are to investigate inference gained from multimodal ensemble predictions by including all available models. And we want to undertake sensitivity testing in order to better understand the reasons behind our models. So I'd like to thank you for your attention, and I hope you've enjoyed this virtual presentation. So I'll hand this back to Hannah for the questions.
Thanks, Maeve. That was a really great talk. We've had a few questions already submitted, so if anyone else has questions that they would like to have answered by Maeve, please pop them in the Q&A box that you can find at the bottom of your screen. Alternatively, you can also raise your hand and I'll be able to unmute you so you can ask your question in person. So I'll just jump in straight to our first question, if that's all right, Maeve.
Yeah, sure. I can't see the box.
Okay,
I'll try and find it.
It should be at the bottom of the screen. The first question is from Graham. Do the conditions used to drive the physical model to produce the surface currents include uncommon events such as the 80 miles an hour wind that resulted in the loss of the Sentinel cage?
Great question, Graham. So one of my colleagues is currently rerunning the simulated one of my colleagues is currently rerunning the exact conditions that were available from 2011, 12 and 13. Now she's having to go back in and be a bit of a detective to find historical data that will help us to run those models. So when that hydrodynamic model is ready to go, we will be able to see what level of the extreme weather events are included. The idea of having individual yearly runs will allow us to get better information on these discrete kind of differences in comparison to the climatology, which wouldn't so we have two different versions of the Scottish Shelf model. We have the climatology run, and then there's some discrete time periods where we have individual runs from. So I don't run that model, so I don't know exactly how much of those 80 mile per hour winds will be included in the run. But the idea of having yearly runs is to be able to see those temporal differences better than in the climatology which is an average.
Okay, great. Thank you. The next question is from Clive. Do you feel for whether bigger differences may result from differences in biological parameters or between the different physical models, or is it too early to know?
That's a really interesting question. So we have to test all of these things. So the first step will be to test the differences in the particle tracking models, hydrodynamics, and that's the first step that we're going to work on. And once we understand the differences between the different particle tracking models and the difference in inference that we get from that, then we will look in how different hydrodynamic models will affect the underlying biology. That's a slightly more complicated thing to do because the grids are different, and there's a lot more work that's required to be able to compare those effectively. I don't know exactly how it's going to look and whether we will get more differences using different physical characteristics or biological characteristics. So that's why we're doing this research.
Great. Our next question from Mark. The high, medium and low particle densities that you showed in one of your previous slides, how does this relate to actually levels of infection found in the farmed and wild fish?
Yeah, so the reason I've shown this as high, medium and low is because when I release particles from a site, I'm releasing virtual particles or superparticles, which are representative of where the particles will end up. And one of the things we do is then weight that according to the consented biomasses on the different farms to try and get a better idea of the abundance of lice across the system. Now, lice tends to be quite patchy in terms of its distribution in the water column. So the reason I've used high, medium and low is just to kind of show a visual representation rather than to talk about the exact numbers. And we do weight it according to the farmed biomasses, and then we use the data collected both in the Sentinel cages and the farmed data from that time to see how good our model is. So that's all work that I'm doing currently.
Okay, so kind of building on that, do you have information on the seasonal variations as well?
So seasonal I'd need more information on that question, Mark. Seasonal variations in lice densities or in hydrodynamic conditions. I suppose we have both. We do have information on lice densities monthly. We do have information on the hydrodynamic in terms of the physical conditions, but I'm not sure if that answers your question, Mark.
Well, if he has a follow-up, he can always type it in to the Q&A as well. 3 questions from John. Okay, the first one is saying, you said the sea lice were low in 2011, but what stage were the farms at in their production cycle? Marine Scotland Science's work in Loch Irae shows that sea lice have a much larger impact on wild sea trout in the second year of production on adjacent farms. Has this been factored in?
Oh, great question, John. So this is part of a 3-year study. So we will look at 2011, 12 and 13. So we would hope to capture all aspects of the production cycle from that by the time this project is finished. So, but if you're interested in this work, quite a lot of this has been previously published by Samala et al. And if you take a look at that research, you might get some interesting information from that.
And of the two graphs that you showed about I think comparing the two models, which of those two graphs showing dispersion distances showed your work?
Okay, so I've pulled up that slide again. I have my information on the left-hand side in color, and then the previous work is in black in the right-hand side.
Thank you for clarifying that. The distances travelled by larvae show that there are high levels in Loch Linnhe and the Sound of Mull, where there are other farms. Will Marine Scotland Science be in position to look at these cumulative impacts?
That's a great question. Within the remit of this project, that's slightly outside the remit of this piece of work, but we do look at dispersion of larval or the dispersal distances of larvae, and we do look at these from kind of a more holistic approach. So while it's not within the remit of this project, it is something that we are interested in.
Great, thank you. We've reached the end of, oh wait, no, another question has just come in, don't worry. From Alan, you spoke about sites being sinks or sources. Is it possible to establish the lice loading threshold at a given site to define the point where it is becoming a problematic source for its neighbours or for the whole system as a whole to enable site-specific action levels?
Eventually, that's something we would like to be able to get towards, but at the end of the day, all of these are models. They are not the truth. They are just the best idea we have of what's happening in the system. So there's a lot of other work that's required in terms of understanding that we're making sure that we're using the best possible models to help us get to to get as close to the environmental conditions and as close to what our data collected tells us. So yeah, it's I'm going to pull that question up to make sure I have answered it. So
You'll just find it under the answered tab.
Possible to. So yeah, it's the sources and sinks of lice are something that we are interested in, and being able to distinguish where lice is coming from and where it's ending up is important. And using a hydrodynamic model, we can make inference about what's happening, and that would potentially enable site-specific action levels. But we're not quite there yet.
And we had one more question to answer today, which came in just at the end of the session, so we're answering it now in this little additional section. The question, Maeve, is this type of coupled modelling also suitable for modelling impact on benthic PMFs? If not, what are the differences? Maeve, if you could also explain what PMF actually stands for, that would be really helpful for our listeners.
So a benthic PMF is a benthic priority marine feature. And this is a good question. So this type of model can be used to simulate the release, dispersion and fate of waste particles from cages. But this would be a job for my colleagues at SEPA, who use a different particle tracking software coupled with a different hydrodynamic model to do this. Currently, they use a model called Meadhbh. So the model will be slightly different in terms of the information in the particles, for example, because waste is passive, but lice are active. But the underlying principles will be very similar in terms of the modeling framework that I've described here today.
Thank you for answering our final question, Maeve. Do you have any final comments after your talk?
Well, I would like to just give a shout out to all our younger listeners. We got 12 fish, so that was really good. And there was 4 boats up until the last slide, but we all lost count because it was a little bit dark. But well done to you guys. That was very clever. I'll have to call on you guys for our next sampling regime when we're all looking for lice on those fish, because we did have one person email me to tell me they found the lice too. So that was very clever. Well done.
That's great news. Thank you so much. And we look forward to hearing from you in your future work, Maeve.
Okay, thank you, Hannah.